Hi everyone, thank you for joining. My name is Nazir Khan and I'll be giving a talk on the, as you can see from the title, the under-inhibition potential of regenerated monoethylene glycol. So in this study we have used a regenerated MEG from an actual plant and it's about 30 years old MEG. So to the best of our knowledge, this is the first of its kind work that we have done, and there's no work related to this type of study that we have done. So before I should begin, so a bit of about myself. I did my undergraduate from Pakistan in the year 2015. Came to Australia for higher studies, did my master's in chemical engineering. And here I was fortunate that I got into this research group under the supervision of Professor Zachary Amen, and where I did a research project. So basically, I was working as a research assistant with some of you might know Shane Morrissey, our previous PhD. So I was basically working with him on a study where I was looking at the Hydrate interparticle cohesive force using biocompatible anti-agglomerants. And that study sort of led to the foundation for my PhD. And currently I'm in my third year, basically looking at a similar research area, I would say, but on a more larger scale, like using high pressure Sapphire Autoclave. So, so far in the past about 2.5 years, I've been able to generate some publishable results, including an almost ready publication work, which was just presented by Ashish on the BG. And second paper is going to be on the work that you are going to see in this presentation. In addition to that, I had been involved in a bit of teaching in the field development unit, again, taught by Professor Zaki Aman, where I was basically demonstrating Eclipse and pattern tutorials in the field development unit. So yeah, that's a little background about myself. In the end of this presentation, what you are going to see is that the regenerated MEG actually does not lose its efficacy, and this is something that you would be expecting, given that if the regeneration MEG plant is working efficiently within its standard. So and this was actually confirmed from our high pressure micro differential scanning calorimetry. And secondly, the regenerated MEG that we are using contains some contaminants in the form of surface active chemistry, which basically we observe significant reduction in the oil-water interfacial tension. And thirdly, and this is going to be the main focus of our talk today, is that the contaminants actually improved hydrate transportability. And this was actually consistent in both a relatively very simple system where we use pure methane as a hydrate former, and also gas mixture system where we had some ethane, propane, and butane. So just by look of the two samples at 10 mg%, you can see that there is something in our regenerated MEG that is causing the discoloration. Now, questions that arise here is, how does regenerated MEG actually perform compared to fresh MEG? Does it retain its efficacy? And secondly, what is that is causing the discoloration in regenerated MEG? We think it may be some kind of surface active contaminants, and if they are, then how do these contaminants affect hydrate inhibition performance, for example, growth kinetics as well as transportability, if we are dosing at mildly under-inhibited concentrations. Now, let's first look at the impact of regenerated MEG, the performance of regenerated MEG compared to fresh MEG, and also looking at what is in our regenerated MEG. We think it's some kind of surface active contaminants. We're going to prove it using some experimental work. So this was the same experimental setup that was just explained by Ashish, but just to briefly explain, so this is a multi-cell micro differential scanning calorimetry, so which allows us to detect hydrate phase boundary condition. So a typical hydrate for formation cycle looks like we load our samples, seal it, pressurize it to the target pressure. In this case, we use pure methane at 10 megapascal. We can control our temperature using Peltier effect, so that can give, and the temperature ranges about -40 to as high as 150 degrees centigrade. We usually cool the system as fast as possible. And once we have form hydrate, this is where we are particularly interested in, because we want to know the hydrate phase boundary condition. And the best way to know is through this setup where Once we form hydrate, we heat the system up, and as we heat the system up, temperature rises, and if there's ice or hydrate, is going to melt, and that's how we actually measure our hydrate phase boundary condition. The fact that it's a multi-set geometry, we can then generate a large number of data sets in a relatively small amount of time with quite good repeatability. So the temperature at which, so the intercept between the baseline and the point at which it starts discontinue these peaks, also known as the, for example, in this case, is our latent heat. We actually operated this experiment below 0 degrees centigrade, so were expecting some ice formation that melts here, and if you have some stable hydrate in the system, is going to melt. So that's actually quite close to what is predicted by models, which I'll show you in the next slide. So this is what the model predicts using CPA InfoChem equation of state if you have no MEG in the system, compared to the result that we generated from our DSC. So we can see that are quite in line with the prediction. We know that MEG is a THI, initial hydrate phase boundary condition. So this is what the multi-flash model predicts. And if you compare with the result that we actually generated through our DSC, that are quite close. And so based on these results, we can quite confidently say that the regenerated MEG actually performed quite similar to fresh MEG in terms of its hydrate inhibition potential. Now, in order to understand if there is some kind of surface active contaminant in the system, so we have used an oil-water interfacial tensiometer apparatus using this hook needle IFT technique. So it's a fairly simple setup. We create an oil droplet inside our liquid aqueous phase, which contains some amount of MEG, and the system has a camera recorder which then detects the dimension of the droplet, and then based on some input information in the form of density difference between the two phases, it calculates the oil-water interfacial tension as a function of time for us. For example, this is what the pure water baseline looks like if you have no MEG in the system, no regenerated MEG in the system, or any. And if you have little bit of regenerated MEG in the system, so what you see is that the IFT drops, as well as if you compare the baseline, it slowly relaxes compared to when you have some MEG in the system, the relaxation time actually decreases. And if you have more of our regenerated MEG in the system, you can see that the IFT drops quite significantly. So this indicates there are some strong surfactants in our regenerated MEG. And interestingly, that we observed was that at above 1 weight%, the oil droplet actually detached from the hook needle. So we were not able to actually run experiment for longer time. Now, if we look at the data across a larger set of trials, typically we run experiment for at least 4 trials. And what we see here is that the results are quite consistent as a function of regenerated MEG. So you can see that there is significant reduction in the IFT. If we compare with the IFT with the pure MEG system at about 5 weight%, so these are 5 and 10 weight%. So the 5 weight% with fresh MEG actually resulted in only 25% reduction in the IFT, and that's the normal surface activity of fresh MEG. Whereas the same amount of regenerated MEG actually resulted in significant reduction. So we see that. So we are confident that there is definitely some surface active contaminants in addition to just the normal surface activity due to MEG. And these results are quite in line with the current generation industry AAs. So that the fact that it's quite in line to the industry AAs, it then tells us that these surface active contaminants actually are can be it can be like an anti-agglomerant. So in order to understand if these contaminants, how does these contaminants actually perform at under-inhibited condition and in the pipeline conditions, and whether they're acting as an anti-agglomerant, we then use our high-pressure Sapphire Autoclave technique. I'm pretty sure that a lot of you will be quite familiar with this setup, also explained by Ashish earlier. So essentially, we have a 1-inch Sapphire cell connected to a mixing geometry, which is connected to a motor through some magnetic coupling. We can run experiments in the pipeline condition. For example, these were the conditions that we used. This is the phase 1 of the project. We kept our system in quite simple in terms of using like the gas hydrate former, just methane, and also gas mix system. And also we use deionized water and mineral oil. In this experiment, we kept our subcooling around 10 Kelvin and constant mixing speed. So mainly we are looking at the hydrate growth using pressure data and transportability or resistance to flow through our motor torque. So if there is some kind of anti-agglomerant in the system, we think that the motor torque signal is going to help us understand, what it's like to have some additive in the system that are acting like an anti-agglomerant. So ideally, you should be expecting almost no difference in the motor torque if it's acting like a strong anti-agglomerant. So this is the quantitative estimate that we can generate using our setup, and the fact that we have a camera recorder which records visuals during hydrate formation, then we can also understand qualitatively like how the evolution of hydrate during experiment. For example, whether the hydrates are in the gas phase, whether they are in the liquid phase, and if it's in some sort of transportable slurry, or whether they are deposited onto the Sapphire wall. So this is what a typical hydrate formation and dissociation cycle look like in our high pressure Sapphire autoclave technique. So this is our temperature profile in red. So if you cool the system, if we are inside our hydrate phase boundary condition, we're going to form hydrate, is indicated by this drop in the pressure profile, and at the same time we have this rise in the motor torque, indicating that some hydrates are forming, which is why this the motor torque is increasing. And once we have formed enough hydrate, indicated by an almost stable pressure profile, we then start heating the system, and you can see that the signals go back to their baseline. So the rate at which pressure drops, then we can actually calculate our hydrate volume fraction with respect to our liquid content. Now, this is what hydrate volume, hydrate growth kinetics looks like for a pure water baseline if you have no additive in the system. If we have a little bit of fresh MEG, this is what it looks like. If you continue adding, the growth kinetics increase. So this indicates that MEG is increasing the gas water solubility, perhaps. And if we compare with the same amount of regenerated MEG, what you see is that there is a significant difference in the growth kinetics. So the regenerated MEG actually is having a faster growth kinetics, and this is actually in line with the result that we just saw in from IFT. For example, if there's a drop in the IFT, it's going to help disperse the system, and this is also shown from these visuals. So again, the red color is our red oil soluble dye. So just to differentiate between mineral oil and water. So this pure MEG, you can see an almost stratified flow regime versus a fully dispersed system. So, and that basically means that you have greater surface area available for hydrate growth, which is why the growth kinetics is faster. Now, typically, a high growth rate is associated with more severe hydrate plug. In order to understand whether we are forming any plug or whether the system is, we are helping the system or making it worse. So the way we understand that is from this hydrate transportability data, or also called fractional change in torque, which is nothing but a relative torque. So the torque increase after hydrate formation. So this is what the baseline looks like. So you can see that as we form around 10 to 30 volume percent of hydrate, there's some kind of fluctuation that indicates that there is either some kind of deposition or some plug formation. And if you continue forming hydrate, the torque signal increase even further, so indicating something bad is going on. Perhaps the hydrate plug is forming. If we have some fresh MEG in the system, you can see that the overall transportability slightly improves. However, we would like our system to be less than, the maximum fractional change in torque should be less than 1, and this is based on the criteria that was set in the beginning using non-plugging oil, where we saw that despite forming hydrate, the system was quite transportable. So if you compare with the 5 to 10% of regenerated MEG, what you see is that there is significant improvement in terms of the transportability as indicated by this relative torque. So we're talking about maximum of 1-ish fractional change in torque. So Now, this indicates that despite increasing the growth kinetics, the regenerated MEG actually improve hydrate transportability. So this is pure methane system. What is going to be its effect on in a more complex hydrocarbon phase system? For example, we have a gas mix system where we have some ethane, propane, and butane. What you can see compared to pure methane system, the difference is that overall the growth kinetics is faster. And mainly there are two reasons. First, we have some propane, and based on some literature, it says the propane actually promotes hydrate growth. So this makes sense because even in the pure water baseline, the growth kinetics is faster than what it was in pure methane system. Secondly, just to remind you that this system is actually all of the gas mix system were performed at a constant high subcooling of 10 Kelvin versus the pure methane where we had 7.5 Kelvin due to the effect of THI due to MEG. So yeah, this makes sense. But if you compare the transportability data, again, you see, if you look at the green data set, that's our regenerated MEG, you see that the transportability is quite improved. Not just compared to pure MEG system, but also if you compare with the pure water baseline, also comparing with the pure MEG system, we see about 2 times low change in torque, maximum change in torque. So now let's look at the effect of increasing amount of regenerated MEG in our system. So we see that as we inject more and more of regenerated MEG in the system, the growth kinetics slightly increase, and this is again consistent with the IFT results. All of these experiments are performed at high 10 Kelvin of subcooling. But if you look at the transportability data and also compare these visuals, what you see that as you add more and more of regenerated MEG in the system, the transportability improves, and especially if you look at the red data sets, that's almost a stable torque profile, and the maximum change in torque is about 0.6-ish. And this agrees well with the visuals. For example, this is our 28% regenerated MEG, where we see almost no deposition, and the slurry is quite transportable, versus you have a massive wall deposition and hydrate plug forming in the case of pure water baseline. This system at 28%, we actually, based on the condition that we perform, would have actually required about 2 times more MEG. So we are basically talking about 50% less MEG and still able to generate a transportable slurry. So we see that there may be significant potential in, if we reduce the MEG dosage in mildly under-inhibited conditions. Okay. So this is where we are at the moment. Like I said, that's the phase 1 of the project. We are going to explore further. So basically looking at the effect of more complex hydrocarbon system, for example, using condensate and crude oils. And also understanding the transient transportability during shutdown and restart. And also the fact that we do have some hydrate in the system. So it's interesting to know how the dissociation kinetics look like if you have some regenerated MEG in the system. So this is where we are looking forward to. Now, coming back to the conclusion, yes, the regenerated MEG actually did not lose its efficacy based on the DSC results. And secondly, regenerated MEG actually contains some surface active contaminants, which resulted in IFT reduction. As a result of that, the growth kinetics was faster, but despite increasing the growth kinetics, the transportability was significantly improved, as indicated by the reduction in the torque signals. And again, that was consistent in our gas mix system. Yeah, so that's the end of the presentation. I would like to take this opportunity to acknowledge the support that I've been receiving from my supervisor panel, in particular Professor Zachary Amen, Dr. Ashish Kumar, and Dr. Bruce Norris.